Okay, so up to this point, you've learned how to differentiate functions that are expressed in what we refer to as explicit form. And explicit form is where you can get y by itself and x, or your independent variable, is on the other side. Okay, that's an explicit form. Now we're going to take a closer look at relations written in implicit form. So if you did the conic sections last year, did you do that in Pandemic World? So you did the ellipse, hyperbola? Yes, okay, you would have done those. Those are impossible sometimes to get y by itself. So, or there are other equations that are just difficult to get y by itself. So I want you to take a look at the box here. On the left, in orange, those are explicitly written forms, so y by itself, or f of x. On the right side, these are what we refer to as implicitly written equations. Do you see it would be impossible to get y alone? It's just literally algebraically impossible. Likewise, in that second one, it is impossible to solve for y. So, we are going to come across these implicit equations, and we have to learn how to differentiate them. So if you look at example 1, if I want to find the derivative of x cubed with respect to x, we know that's 3x squared. But watch this in letter B. This is where the explicit comes in. If I want to take the derivative of y cubed with respect to x, this is going to be bring down the power, decrease the power by 1, and then you're going to have to take the derivative of whatever y is with respect to x. And if you think about it, I really could have done that same thing here, take the derivative of x with respect to x, but what's dx dx? It's 1, okay? So then, look at letter C. If I want to find the derivative of x plus y with respect to x, that would be 1 plus dy dx. So kind of the big idea here, the only addition to implicit differentiation is that any time you have a y, you're going to have to include the derivative of y with respect to x. That's the only new part to this. And then you'll be able to isolate the dy dx to differentiate. So then look at letter D. So this is where it gets really fun, is I have the product rule. So I have xy squared. So I'm going to do the first times the derivative of the second. So that's 2y dy dx plus the second times the derivative of the first. We would just tidy that up a teeny tiny bit and say 2xy times dy dx plus y squared. And I don't know why it is, but I just love doing implicit differentiation. I just find it super fun. So here are your guidelines. You're going to differentiate both sides of the equation with respect to x, collect all the terms that have dy dx, and move them to the left side. This is the typical way the multiple choice question answers go, because you technically could move them to the right, but then you have to do some extra manipulation to get it to look like their answers. You move all the other terms to the right side of the equation. Factor out dy dx, and then solve for it by dividing any remaining factors. So let's just get to work here. In example 2, if I want to find dy dx, so watch what I'm going to do. This is going to be 3y squared dy dx plus 2y dy dx minus 5 dy dx minus 2x. What's the derivative of negative 4? 0. The derivative of a constant is 0. So this is cool. All of our derivative rules work, like the product rule, the quotient rule, the chain rule. All right, so I'm going to multitask here, and I'm going to factor out the dy dx, and I'm going to move that 2x to the other side. Can you handle doing both things? So we're going to factor out dy dx out of the terms that have it, and I'm going to move the 2x to the other side. Then here's what I mean by divide both sides. So I'm going to make that dy dx would equal 2x over 3y squared plus 2y minus 5. So what's really interesting is that even though in the original equation, the implicit equation, I could not get y alone. But going through the technique of implicit differentiation, I can determine the derivative. Okay, so that is interesting. So let's look at example 3. It says, consider the equation x squared plus 4y squared equals 4. It says, sketch a graph of the relation on the coordinate plane provided. So if you have your graphing calculators, I gave you some steps here. So from pre-calculus, this is an ellipse. So I gave you 3 methods on how you could, on the TI Inspire, graph this. So you can press menu, option 3, graph entry, press option 2, relation, type it in just as you see it. X squared plus 4y squared equals 4. Hopefully that works. The method 2, you could try this one. It says on a graph page, enter f1 of x, and you type in zeros, parenthesis, x squared plus 4y squared minus 4 comma y. It doesn't work, it says, with very complicated ones. Method 3, on a graph page, press menu, 3, graph, number 3, equation templates for ellipse. Yeah. So worst case is, like, if you recognize that this is the equation of an ellipse, like I just graphed some points, and I got my 2, 0 worked, negative 2, 0, 0, 1, negative, or 0, negative 1. I knew just from the equation that this was an ellipse, that if you divided by 4, so I knew my center was at 0, 0, and that I had vertices were at plus or minus 2 comma 0, and the co-vertices were at 0 plus or minus 1. So again, you didn't have to do it on the graphing calculator. You could have done this by hand. Anybody else getting it? I wonder if this is for the C8F, so we have the CF. I bet you that's it. Right, that's what I think. We'll have to play with it, but like I said, you don't have to be able to use the graphing calculator. We'll have to play with that a little later, try to iron that part out. But for now, let's just get to our doing the derivatives here. So this is an ellipse. You should recognize from pre-calculus that that was the equation of an ellipse. If you need to do a little conics review, you can Google and work on that. But let's go ahead. If you want to find the derivative of that ellipse, you're going to do the derivative 2x plus 8y dy dx equals 0. You want to get the dy dx on your left side. And then when I divide, that'll give me negative x over 4y. So now what's super cool is we can find the slope of the tangent line, but you need an x and y coordinate most often when you're doing implicit differentiation. So then my slope is going to be dy dx equals negative square root 2 over 4 times that y value. Okay, so we have a bunch of yucky fractions. Can you see that the negatives are going to cancel? Okay, then 2 negatives are going to cancel, and I have square root 2 over 4 over square root 2. Then when you divide by a fraction, that's the same as multiplying by the reciprocal. So that's 2/4. Oh, that worked out nice. That was 1/2. Then we can write the equation of the tangent line. So that's y plus 1 over the square root of 2 equals 1/2 times x minus square root 2. So we can write the equation of the tangent line to the curve at that particular point. All right, now we want to show how, in fact, these are the same. This one, I could, in fact, solve it explicitly. If I look at x squared plus 4y squared equals 4, I could subtract the x squared, and I could divide by the 4. Oh, I'm going to rewrite that because that does not look. Let's write it like this because I forgot that I had to do a square root. So do you see that this is going to be y equals plus or minus? And let's make that the square root of 4 minus x squared all over 2. So then let's do the derivative. So if you brought down the 1/2 with that 2, do you understand that would be 4? Times, and the derivative of the inside is negative 2x. Well, that minus with the plus or minus, it just would flip it to minus plus, which is the same thing. So that's plus or minus. I would have, that 2 would cancel. And I'd be left with x over the square root of 4 minus x squared. Now, let me go back up to what we had. We said dy dx equaled negative x over 4y. Now watch this. This is like super cool. We know what y is, right? Y was plus or minus the square root of 4 minus x squared over 2. Oops, sorry, I was like, wait, these are supposed to be the same. They're not. I lost my 2 there. There we go. So then look, that does give me plus or minus x over 2 square root 4 minus x squared. So if you can do it explicitly, you want to do it explicitly. But implicit, I think once you get the hang of it, it's really simple. Yeah, look at
How do you, on the top right hand side, plus or minus 24, how do you get 24?
Oh, do you see here's a 2, and then I brought down the 1/2. I'll put the step in. Sorry about that. So watch. Yeah. So this is 4 minus x squared to the 1/2 power, and let me pull that 2 out, this 2. So then when you bring down 1/2 times 1/2, I mean, that's a great question. That's where the 1/4 came from. Sorry, I could have written that out. Then it'll take you back up here, okay? So this 2 is the 1/2. Then when I bring the power down, that's where the other 1/2 comes from to create the 1/4. Okay, great question. Any other questions? All right, so let's look at example 4. So what I just showed you in example 3 is I can do it explicitly or implicitly when it's possible to do explicit and show that the derivatives are in fact equivalent. So in example 4, it says find the slope of the graph of 3 times the quantity x squared plus y squared, the quantity squared, equals 100xy at the point 3, 1. And I went ahead and sketched it using Desmos. So I'm going to pause a moment because this one's a fun derivative to do. Let me give you a head start. Go ahead and see if you can find the derivative. When you find the derivative, then plug in that x is 3 and y is 1. And then that will be the slope. So find the derivative. Here's how we do. You're going to have the chain rule. You're going to have a product rule. You're going to have some fun times here. Yeah, the 100xy is going to require the product rule. What I would recommend is keep the 100 with your x, consider that as a factor, and then your y. So one of the reasons why I like implicit differentiation is it's challenging, but it is so satisfying when you're done and you get it. Like that to me feels fabulous. For those of you that are pretty far along, when I reduced, I got 13 over 9. 13 over 9. All right, I'm going to start it. Here we go. I'm going to bring down the power. I'm going to decrease the power by 1, and then I'm going to do the chain rule. That's 2x plus 2y dy dx. Okay, how many got that part right? Show hands. You got it? All right, then we're off to an awesome start. On the right side, I'm going to take 100x times the derivative of y, which is dy dx, plus y times 100. All right, show me hands. Did we get that? All right, so we didn't quite get all the way there. All right, so I'm going to do this one nice and slowly, putting lots of steps in. So I'm going to first distribute. Oh, you know what? I'm going to show you something. I'm not gonna do any simplifying right here. Okay, I'm going to show you a technique. I only needed the slope, correct? Watch this. I'm going to rock your world. X is 3. Yeah, we're going to plug in right away. And so you'll get 3 squared plus 1 squared. That would be 6 plus 2 dy dx equals, wouldn't that be 300 dy dx plus 100? Now, all I need to do is solve for dy dx, and that's not nearly as bad as trying to multiply all that stuff out. You understand that? If I want to find the slope, all I need is to plug in the x and the y and solve for dy dx. That is way easier than trying to solve algebraically for the dy dx and then plugging in. You are allowed to do that. So this is 6 times what? 10? 6 plus 2 dy dx. I mean, it's still a lot of work, okay? It's still, I'm not, but it's less difficult work. All right, so then I'm going to get 360 plus 120 dy dx. and I got 13/9. The negatives cancel. When you have two numbers that end in a 0, like that means it's divisible by 10. So then you're looking at 26 over 18. 2 goes into 26 13 times. 2 goes into 18 9 times. All right, not too bad, but I did want to show you that's sort of a more efficient way to find slope. All right, we have something called logarithmic differentiation. It's not tested on the AP Calc exam. However, I've seen it somewhat sneak in somehow that it's a little bit easier to calculate. So I'm going to go ahead and show you this. If you look at A, B, C, and D, which of these can you find the derivatives of? I'm going to give you a quick head start on me. Which ones can you find the derivative if you can find it? Be careful. What's a constant and what's a variable? And I'll give you a hint. There's only one you cannot do. All right, letter A, did you get 0? Because e to the e is a constant, okay? E to the e is a constant. B is e to the x. Now, in letter C, you actually can do this one. X is your base, and e is a number. So that applies to my power rule. So you bring down the power and decrease the power by 1. Right now, we cannot do this one. But I'm going to show you how we can do it. And it's called, and I've been actually showing you this. So look at example 6, and then it'll roll back up and we'll talk about letter D again. We can do what's called logarithmic differentiation. You understand why the power rule doesn't work in letter D? What does the power rule say? Maybe we need to fine tune what our power rule is. Why is this not the power rule where I bring down the power? What does the power have to be? A constant, okay? It has to be a real number. So you can't apply the power rules. This is really, really good for us to distinguish here. So now I can take the natural log of both sides and then use that power rule. Now take the derivative of both sides. So that's 1 over y dy dx equals the first times the derivative of the second plus the second times the derivative of the first. So anytime you have a variable in your exponent, you can, in fact, do logarithmic differentiation, where you can find the natural log of both sides. So that's 1 over y dy dx. Here the x's cancel, and I get 2 plus 2 natural log x. But then you're going to multiply both sides by y. And we know why. Y was x to the 2x. So let's go back up here. If you did do it now, this one is x to the x times 1 plus natural log x. And you could work it out again if you'd like. All right, so in my think about it, how could you do the derivative of y equals 2 to the x? I already showed you that. Yeah.
The base is a constant and the power can be variable, but if the base is a variable, then the power can be a
Okay, the power rule has to be y equals x to the n, where n is a real number. That's the power rule. If I have exponential, that's different. If I have 2 to the x, that's completely different. That's not the power rule. Okay, great question though. All right, so let's look at example 7. It says, find the derivative of y equals x minus 2 the quantity squared over the square root of x squared plus 1 using logarithmic differentiation. So watch this. I could do the natural log of y equals the natural log of x minus 2 squared, and I'm going to go ahead and be proactive because I know where I'm headed, and change that square root to the quantity, the 1/2 power. And we did one like this earlier. It's very, very simple to find the derivative of a natural log. It's 1 over the stuff times the derivative of the stuff. But what you need to do is get it so that you have a natural log of just one thing instead of a quotient. So let's split this using our log properties. How are we doing with remembering log properties from Algebra 2? Can you give me a quick thumbs up, out, or down? Like, do we need, all right, so what I'll do is I'll put together, because we have some time, Wednesday, Thursday, I'll put some extra practice just to build up. Yes, we have a quiz on Friday. And so today we're done now with all the new content. So we're not going to do anything new tomorrow or Thursday. So we're going to spend 2 days reviewing. So don't panic if you feel like, oh my goodness, implicit differentiation's tough. It is tough, but we're going to get it. You will get it. So now I'm ready to differentiate. So this is 1 over the stuff times the derivative of the stuff. So this is 2 times 1 over x minus 2 times 1. So I'm going to put the stuff down with that 2. Oh, do you see? This is not the derivative. Yeah. Yeah, I was not taking a derivative there. I was still using my power property for logarithms. I know, and that's tricky. You're like, okay, wait a minute. I brought down the power. Well, that was not a derivative. That was the natural log of x to the p. You bring down the power. That's just that property. Okay. So then I have 1 over y, dy dx. Let's tidy this up. Then I need to multiply by y to get dy dx alone. And y was x minus 2 squared over the square root of x squared plus 1. So very ugly answer. And again, what I mentioned yesterday is sometimes when you're doing this technique and you could have done 1 over the stuff times the derivative of the stuff, final answers could look differently where they build a common denominator and simplified. That could be another possibility. But typically they prefer you to do logarithmic differentiation and then leave it like this. All right, questions? Yeah. You do have to plug it back in, yes. Yeah, because you need dy dx alone, and it's in terms of x.